Welcome to lesson number 1 on exponential functions. We're going to begin by looking at the exponent laws, starting with the product law here. Now, with my product law, I have x to the power of m times x to the power of n, where my base is the same, and I have different exponents. And so, with the product law, we add our exponents. This would be x to the power of m plus n. The quotient law is the reverse, and if I'm dividing in exponents that have the same base, then this becomes x to the power of m subtract n. Power of the power law. Again, I have one base x, but I have an exponent raising this other exponent. And in order to combine these, I need to multiply my exponents. So that's m times n. With the power of a product law, we need to distribute my exponent into two different bases. So this would be x to the power of m times y to the power of m. Our power of a quotient law is very similar. Again, I'll be distributing my exponent into my bases. However, it's a quotient, so this would become x to the power of m divided by y to the power of m, where y cannot equal 0 because then we'll have a divide by 0 error. My integral exponent rule we use when we have a negative exponent, and in order to make this positive, we would express this as 1 over x to the power of m. Again, where x can't equal 0 this time. And with irrational exponents, we can express this as a radical term, where n becomes my index and m becomes my exponent on my base, or in this case, my radicand. Another way we could express this is the nth power of x times, or to the power of m. Now let's piece these rules together with these following examples. We want to write each expression without brackets and using positive exponents. So first of all, if I have 1 over 2 times y to the power of negative 6, I need to use my integral exponent law here. And so this would become 1/2 times 1 over y to the power of 6, or 1 over 2 times y to the power of 6. Right here, I have 5 times x to the power of negative 3 and y to the power of negative 2. I can simply switch my bases, and I would have 5y squared divided by x cubed. With this problem, I'm going to use my distributive property, and I'm going to combine my coefficients. 4 times 2 is 8, and then I will then combine x cubed and x to the power of negative 4 by adding these exponents. This would be x to the negative 1 and y to the power of 3, which would give me 8y cubed over x. Next, I have 24 times m to the power of 5, p to the power of negative 3, q to the power of 4, divided by negative 4, m to the power of 4, p to the power of 2, and q to the power of negative 2. I can begin by combining my coefficients. I have negative 6, and with all of these variables, I can combine these using my quotient law. And so I'll combine the m's, the p's, and the q's. So 5 minus 4 would leave me with m. Negative 3 subtract negative 2 would leave me with p to the negative 5. And q to the power of 4 subtract negative 2 would give me q to the power of positive 6, which when we put this all together, leaves me with this. My last one here, I'm going to be distributing my 3 into everything in the brackets because this 3 has a 1, an exponent of 1 on it. This would give me 3 cubed, x to the power of 2 times 3 is 6, and y to the power of 9, which would leave me with 27 x to the power of 6, y to the power of 9. And finally, I have 12 divided by 3 gives me 4, and b to the negative 1/2 subtract 1, I'm going to have b to the power of negative 3 halves, or 4 to the power of b to the 3 over 2. Next, we want to, without using a calculator, determine the exact value of the following. We will then verify with a calculator. So 2 to the power of negative 3, we can express this as 1 over 2 cubed, and 2 times 2 times 2 is 8, so this would leave us with 1 over 8. With this next problem, I can express this using my rational exponent law. We would have the fourth root of 81 to the power of 3, which would be 3 to the power of 3, or 27. To the 0 power law, we have 25 to the power of 0, which is equal to 1. And 16 to the negative 1/2, we can express this first with a positive exponent, which would be 16 to the 1/2, which is equal to 1 over 2 the square root of 16, or 1 over 4. Now we're going to look at converting each of the following to the indicated bases. So 9 to the power of 2x to the base 3. In order to express 9 as a base 3, we could express this as 3 squared to the power of 2x. 3 squared to the power of 2x. Then use our power law. We would have 3 to the power of 4x. 125 to the power of 2 minus x to base 5 would become 5 cubed to the power of 2 minus x. We could then distribute our exponents, and so we would have 5 to the power of 6 minus 3x. Here we have 8 times 16 to the power of x to base 2. We would express this as 2 to the power of 3 times 2 to the power of 4x. And then we could add our exponents, 2 to the power of 3 plus 4x. Now lastly, we have an equation with rational exponents. Now, we have two people, Sarah and Lee, and they're looking for the volume of a beach ball. They solve it in two different methods, and the first thing they do is they get their equation simplified to r cubed is equal to this. And so they're at the same step. However, they do a different move in order to solve for r. So what Sarah does is she takes the cube root of each side of her equation. Now, when she takes the cube root of each side of her equation, what she ends up getting is something like this. So first of all, she has 3 times 50,965 divided by 4 pi. And then she does her cube root, and actually I'm going to store this answer A, and she takes the cube root afterwards of alpha A, and she'll get 23 centimeters. Now, what she did was she cubed rooted each part of her equation. However, what Lee does is he raises each of the equation to the power of 1/3. And so he'll raise this to the power of 1/3 and this to the power of 1/3. And we'll see what he gets. So I simplified the part that they both got. So alpha A. And I'm raising this now to the power of 1/3. And he gets the same thing. He gets an answer of 23. Now, either step is correct. The only difference between, and actually you're carrying out the same operation in each case. The only difference is the form of cube root or third power that is being used. So Lee uses to the power of 1/3, which is just the integral notation of r cubed, or sorry, the rational notation of r cubed. Last, if we want to solve one of these expressions, I could carry out Lee's method, where I raise it to the the opposite powers, so 3x minus 5 to the power 3 halves, but raise this to 2/3 power is equal to 27 to the power of 2 over 3. On this side, those exponents will cancel out, and we'll be left with 3x minus 5. 27 to the 2/3 could also be expressed as cube root of 27 squared, which would be the cube root of 27 is 3, squared is 9. 3x is equal to 14, and x would be equal to 14/3.